Let's look at this separable linear DE, this IVP, initial value problem. So I've got this DE and I claim it is separable. We can see that if we factor a y from this right-hand side and then divide that y to the left-hand side, divide the x squared to the right-hand side, we can see I can get all my y's over to the left, all the x's to the right. Now, here's the math that's going on in the background. What we're actually doing at this step is we're integrating both sides with respect to x. Remember, you will never in your life write this integral symbol without also having a differential that you will usually write because it won't be there. You cannot write an integral without a differential to go with it. Those symbols go together. So we are technically integrating both sides with respect to x. But by chain rule, dy dx is just dy. That's just u substitution chain rule. So the left-hand side, we're going to end up integrating with respect to y, and we integrate the right with respect to x. And that should seem a little weird to you, that we're integrating with respect to two different variables. We're really not, we've just used chain rule. Now, the hand-wavy way we're going to do this from now on, we're not going to write out this step here. We're going to pretend like I can just pull this dx over to the other side. This dy dx is not actually a fraction. This is the limit as delta x went to 0 of delta y over delta x. We can't really multiply the dx over. But because of chain rule, it kind of turns out we can pretend we can and just ignore that and do it. So the way we'll write this from now on is we'll multiply, in quotes, the dx to the other side and then just integrate both sides and get this. So we're going to integrate this guy with respect to y, this guy with respect to x. Now this integral here is much easier if we just split that numerator and do each of these terms independently. So the antiderivative of 1 over y dy is natural log absolute value of y. And then over here on the right-hand side, we get this. Technically, we get a plus c from each of these three, but we just squish that all together into one constant of integration. So here's our implicit solution. If the question asks for an implicit solution, we're done. That's it. Let's plug in our initial value, y of 1 equals 1. Remember, natural log of 1 is 0. So you can clearly see what we get here. We get c equals 1. Here's our particular solution. Now remember, this is an implicit solution. This is not a function in the sense that this would fail the vertical line test. Y is not an explicit function of x. This is actually two different solution curves in the xy plane. One for positive y's, one for negative y's. And those are actually separated because we have a domain issue. X is not allowed to be 0. But if we want y as a function of x, then we need to pick one of our solution curves. It's that absolute value of y that's causing the issue. So let's pick what we call the positive branch when y is positive. And just so we don't have to deal with domain issues, we'll choose x as positive as well. And we'll find an explicit particular solution here. So starting with our implicit solution. Since y and x are both positive, we can drop those absolute values. Now we can write both sides as powers of e. I want to get rid of that natural log, so I'm going to make both sides powers of e. E and natural log are inverse functions. They cancel out. We just get y. On the right, I have e raised to this entire thing. Now, by rules of exponents, remember, a to the m plus n is a to the m times m a to the n. Rules of exponents say I've got all this stuff added in my exponent. I can make same base and all those multiplied. Okay, let's look at this guy right here. I kind of want to cancel the E and the ln, but I can't do anything yet because I have that negative there. So rules of log say that -1 can come inside and make this x to the -1 power, which is 1 over x. Then e raised to the ln of junk is just junk because those are inverses. This guy right here, e to the c. A number raised to an arbitrary constant is just a different arbitrary constant. So I don't have to carry around an e to the c. I'm just going to give it a new name and call it capital C. And we could have, we're going to do this a lot this semester, I could have just said, you know what, forget it, e to the c is just c. And I could have kept the same little symbol c, and that's fine. I'll show you where you might have issues with that in a minute. But this is just a new constant. Let's give it a name. I called it capital C here. So we get this implicit solution, or this explicit general solution. Now, here's where you got to be careful with your C's. When I go to solve the initial value problem, I'm going to plug in here, I'm going to solve for capital C here, and notice that I get a different thing than I did up here when I solved for little c. That's when it's important. When you're solving an initial value problem and you want to compare with someone else, you might get different values for your arbitrary constant depending on which version you used. However, when we go to our particular solution, it doesn't matter. If I had taken this particular solution here and written this in explicit form, going to go through E, both sides, all that, I would get exactly the same solution as I'm about to get. So using this version, this capital C, we get C equals E. So you want to look at the algebra here. This is E to the -1. To solve for C, I would multiply both sides by E and get C equals E. Okay, we got to use rules of exponents again here. E to the 1 times E to the -1 over X would be E to the -1 over X plus 1. So there's our particular solution in explicit form, and here's what the solution looks like. There's a graph of it. Notice that it does pass through the point 1, 1.